Welcome back to my channel, Predicting the Future. In today's topic, we're going to continue on Markov Chain, and we're going to talk specifically about the asymptotic behaviors of Markov Chain, which many people already know, but we're going to go through some of the important theorems here. So suppose J is a transient state. We know that the sum of the transition probability to the power n from I to j is finite, which means that the p to the power n goes to 0 as n goes to infinity. But what if j is recurrent? When j is recurrent, we know the sum of the power n is infinity. But will the p to the power n from I to j converge? That's something we want to find out. So before we talk about that, I want to quickly go through some of the simple facts about it's also in asymptotic behaviors. So suppose let nj to be the number of visits to state j in n transitions. Then if j is recurrent, then the number of visits to number of visits to state j divided by the total transition n will converge to its stationary distribution, which is actually 1 over the expected value of tj, almost surely. So that's very intuitively correct, because in n steps we know that it's a proportion. It will be the same proportion of steps that will visit state j for every period of tj. Just one visit for every tj, and tj is finite. If tj is finite, then there will be a fixed ratio. When n is increasing, the number of visits to j will also increase in the same ratio. So that will converge to a number. If expected value of tj is infinity, then we're defining that it will be 0. So 1 over expected value of tj will be 0. It's also valid. So next thing I want to talk about is a proposition of this theorem. So suppose xm is an irreducible Markov chain with stationary probability pi j, and another function g, which is a bounded function on the state space. Then as n goes to infinity, the sum of g on value xm over n, which will converge to sum of g taking value j times its stationary probability pi j. So and it's the same of g to the taking value j divided by its expected value of tj. Tj is the expected number of transitions from j to j, from the current j to the next j. And the proof is actually using the theorems we just saw here, and so we can write down this sum of gxn divided by n into the other form, where the g taking value xmn times the identity random variable when xm equal to j. So when xm is equal to j, the summation of all j state is just 1x gxm. So this is the same, and by the previous theorem, we know that this sum of m over from 1 to n of this term will converge to g to the g taking value j divided by expected value of etj. And so that's the proposition from that theorem. And the last thing we want to talk about is the famous one, which is the limiting distribution, which is if P is an irreducible aperiodic Markov chain with a stationary distribution pi, then when n goes to infinity, the probability, the transition probability P to the power n is the n step from I to j, will converge to a stationary distribution pi j, no matter what I is. Well, here, why do we need aperiodic? Aperiodic because we want that limiting distribution, the limiting power, P to the power n, will converge. If it's now aperiodic, let's say it has a period of 2. So for I to return back to itself, it takes 2 steps. Then every even step will be 0, and every odd step will be 1. Then there will be a sequence 0, 1, 0, 1, 0, 1, and it doesn't converge. So that's a necessary condition for the limiting probability P to the power n to converge. We have to have a periodic Markov chain. So that's it. That's I want to talk about for the asymptotic behaviors of Markov chain. I hope you like it, and thank you, everyone.